Now, let's see the other case, when a filter is not properly designed, is a mismatch to the actual physical model, and for this purpose, we assume that the truth, the system process noise, has variance 9, but the model based on which the filter was designed assumes the process noise has a variance Q sub f of 1. So the true Q is 9, the filter assumed Q is 1. Obviously, we are not going to get good results. And if we look at the figure, here, the acceptance regions for the normalized estimation error square is between 0 and 6 or 7, doesn't matter. Majority of the points are outside. So the normalized estimation error square tells us from a single run already there is something wrong. From 50 runs, it should be around 2. None of the points are inside. They're all outside. So you can see that while for a single run, perhaps half or so of the points, a little bit less than half, are inside the acceptance region, even enough of them are outside, so the 95% clearly is not satisfied. In the 50 run result, all of them are outside, so you can see how much more powerful the test is if we use 50 runs rather than 1. This is the normalized innovation square that's already from 50 runs, only from 50 runs. It should be around 1. They're all outside. And look at the correlation between successive innovations should be 0. It's more like 0.5. So you can see that the poor design causes the innovation sequence not to be white, to have a variance that's not like calculated, a much larger variance actually, and same thing for the state. So we have with this a clear indication for Monte Carlo runs that the filter is not operating properly because it's a poor design. Now the question is, can we in real time reach the same conclusion that is something terribly wrong with the design based on a single run? So we look at the real-time consistency test, the single run test that can be performed in real time. First, let's look what is the time average autocorrelation of the innovations obtained from 100 samples for the correct filter. Again, it should be 0, but it's not going to be 0. So one run on the correct one says it should be, what here we get is the average autocorrelation one step apart is 0.15. Now, under the assumption that the filter is correct, the error in this estimate is rho bar is an estimate. That's only an estimate. Is Gaussian, distributed with mean 0 and variance 1 over 100. So the standard deviation is square root of 1 over 100, therefore 0.1. So 1/10. And we can allow 2 such standard deviations. So the 95% probability region is minus 0.2 to plus 0.2 approximately. Therefore, we obtained an estimate of 0.15 by just looking at it. Is it 0? Obviously, it is not 0. Is the 0 acceptable in view of the fact that we get 0.15? The answer is yes, because any number between plus and minus 0.2 is going to be what we'll see 95% of the time from our 100 samples. And therefore the inherent variability is with standard deviation 0.1. Therefore this is within the inherent variability. So our conclusion is the filter is matched to the system, so we confirm what we already knew. In the mismatched case, the estimate is 0.509, and you can see it's way outside this. It also matches the 0.5 obtained from the Monte Carlo runs, but now it's one run and time average instead of 50 runs and ensemble average over the runs. So clearly from a single run, the autocorrelation shows itself as being wrong, therefore there's something wrong with the filter. The other quantity of interest that can be obtained from a single run will be our test for the time average normalized innovation squared over 100 time steps. If we use the matched filter, the result is 0.936, while ideal value is 1. Again, you'll never get the ideal value. When it's 1, you don't get 1. When 0, you don't get 0. Are you close enough to that value? That is the question. And what does close enough means? The answer is based on a statistical confidence or probability region that you have to obtain. So the 95% region based on the 100 degrees of freedom chi-square is 0.74 to 1.3. So this is well within it, clearly. Now, for the mismatched filter, you get a normalized innovation square that should be 1 as 2.66 from the 100 samples in time, and it is way outside this region. It's unacceptable. Therefore, the single run does provide us with appropriate tests the information whether the filter is working okay or not working okay. So we can detect a filter mismatch using suitable statistics and their probability regions. The next topic will be filter tuning, which will provide an explanation as to what really the process noise is accomplishing. In practice, in many systems, we are not given the process noise. We choose a process noise to model the disturbances. You can have, as an example, unknown inputs like target maneuvers in tracking. For an air vehicle, you can have turbulence that's unavoidable. Clearly, this does look pretty much like process noise. However, you can have also pilot-induced maneuvers, and because we don't know what they will be, when they will occur, what we do is we model them as a random process. So, the procedure to match the process noise variance to suitably model disturbances is called filter tuning. Clearly, such inputs like maneuvers are not real noise in the probabilistic sense. So what we do is we design a filter that uses pseudo-noise or artificial noise. So, because we don't know what goes in, we model it as a random process. Because we need white noise, we model it as white noise. That's what the filter needs. Obviously, if it is very different from white noise, you can model it as the output of a subsystem driven by white noise. So those unknown inputs can be modeled as correlated noise as well. So the procedure for tuning is to make the filter consistent. Namely, the three criteria, A, B, and C, should be satisfied. Obviously, this is easier said than done. In practice, one has to strive to make the filter as close to being consistent as feasible, while at the same time achieving small RMS estimation errors. So what we really have to do is do a compromise between adding more noise that will increase the variance of the resulting estimate. Therefore, the normalized estimation error, normalized innovation squared will be smaller, but you don't want them too small either. So what you want is reduce them so they are within the acceptable range, more or less. You cannot always do it, but at the same time you have to take close look at the actual root mean square errors, the unnormalized errors. So the tests use normalized errors divided in a matrix sense by the filter calculated variances. We want them within an acceptable region, more or less, and we want the unnormalized absolute errors to be small. Now, what are the absolute errors? What we are really interested is the absolute performance of the filter, RMS errors. That's a simple way of quantifying them. What we have is also the information that you cannot get small RMS errors if the variances are mismatched. So you look at both of them simultaneously and end up with some kind of a compromise. So what we are going to look now is how to obtain from simulations the actual RMS errors for position, velocity, speed, and course. Remember, speed is the magnitude of the velocity vector, course is the direction of the velocity vector, which is not the same as heading, because whenever you move in a fluid with cross winds or cross currents, heading is not going to be the same as course. So, for a scalar psi, the root mean square error from n Monte Carlo runs with observed errors, psi tilde I in around I. This RMS value is the root of the mean of the squares. So, as the word RMS says, it's root mean square error. So, what you have is in run I a quantity psi I tilde, and you sum the squares, divide by n, take the square root. For a position vector, the RMS position error in 2 dimensions will be sum psi I square plus eta I square with a tilde on each of them, sum over the number of runs, divide by n, and take a square root. For velocity, RMS velocity error will be the same thing. Now, speed, it's a little bit different, because speed is really the true speed is psi I dot square plus eta I dot square root of this. And we can estimate the speed as the same square root of the sum of the squares of the components, where we use the estimates. So psi dot hat square, eta dot hat square. And this will be the estimated speed. Then the RMS is just the difference, ui tilde, which is ui minus ui hat, take them squared, sum over n, divide by n, take the square. So this is the RMS for the speed error. And without subscript u is just a speed now over all the runs. If we talk about the course, and here we have measured in the navigation convention clockwise from north or from the eta y-axis. Theta I is arctangent psi I dot over eta I dot. To estimate the course, we use the velocity, estimated velocity components, and we define these 2 angles. Then the difference theta I tilde is theta I minus theta I hat, and we use the standard expression for the root mean square error of the course coming out of a filter, which is estimating the state vector of an object moving in a plane in this case. Let's summarize the results for filter consistency. This consistency testing is crucial for estimator optimality evaluation. An estimator that is inconsistent is not optimal, clearly. A state estimator is consistent if the first and second order moments of its estimation errors are as the theory predicts. The means are 0 for the errors, or the estimates are unbiased, and the covariance matrices are as calculated by the filter. Compatibility of actual mean square error and calculated covariance matrices. The statistic that tests the mean and the covariance is the normalized estimation error squared NES, It can be done for the state, and it can be done for the innovation. Then we call it normalized innovation squared. Under the Gaussian assumption, these statistics are chi-square distributed and should be with a high probability in certain intervals, the corresponding probability regions, and because they are chi-square, the tests are also called commonly as chi-square tests. If you have bias in the estimates that is significant or error magnitudes too large compared to the filter calculated standard deviations, these will be detected by the statistic. In this case, we can say the filter is optimistic because it thinks it is doing better than it actually does. Its filter calculated standard deviations are smaller than the actual errors. The way we do this test is in the offline or simulation situation for state estimation errors, we have the truth for comparison. For the innovation, we can do it both offline but also online, and innovation is the only thing that is available online. To test the innovation's whiteness, we use the sample autocorrelation, and the magnitude has to be below a certain threshold. This can be carried out offline or online, and again remember what the autocorrelation at two different times has to be exactly zero. You will never get zero. You have to be close enough to zero, and the probability region tells you what is acceptable as close enough. And these tests become very powerful. They can detect inconsistent or mismatched filters when used in Monte Carlo runs. What Monte Carlo runs do is evaluate ensemble averages of the test statistics. Instead of an expected value, you take an ensemble over many runs, over many realizations of the same random variable. And these averages are obtained from independent runs. This is an absolute requirement that no random variables should be reused from run to run in no circumstances. Absolutely all the random variables, starting from the initial error, the process noise, measurement noise sequences, everything has to be all over new, totally independent random variables. So, what this does with all these random variables independent from run to run provide us this significant decrease in the variability and therefore would increase the power of the test. The more independent random variables you have, obviously, the more powerful the test, the easier it will be for the test to detect a mismatch. The acceptance regions defined by upper and lower bounds within which the test statistics should be have been established. Some are based on the chi-square, some are based on the normal distribution. If the normalized error statistic exceeds the upper bound, and this is one situation that can happen, we can have a significant bias in the estimates, or the errors are too large compared to the filter calculated covariances, or the covariance is too small. Really, the last two are different ways of saying the same thing. In this case, we call the filter optimistic. It thinks it's doing better than it really does. And this is very bad because obviously the filter is misleading us. Now, if the normalized error statistic is below the lower bound, then the covariance is typically too large. We are pessimistic, we are conservative. Now, it is sometimes difficult to have never optimistic, never pessimistic situation, because this is one of the problems. The behavior of certain objects is changing drastically in time, and this is why we need, if we have a single model, we cannot accomplish this, never optimistic, never pessimistic. We can get close to accomplishing it by taking multiple models, as it will be seen later in the multiple model estimation algorithms. So, For real-time performance monitoring, we can implement tests based on time averaging, but only for the innovation, and we can do the magnitude of innovation and the wideness of the innovations. Now, one important thing that has to be remembered is initialization. It's a recursive algorithm. Things that start bad can stay bad. So what we have defined before is that a state estimation filter is consistent if its estimation errors are commensurate or compatible with the filter calculated covariances. At the initial time, when we initialize a filter, it is just as important that the covariance associated with the initial estimate reflects realistically its accuracy. So what we have, remember there were three sources of error: initial error, process error sequence, measurement error sequence. Start from the beginning. You have to make sure that at the initial time you already have consistency. Otherwise, the filter is misled by the initial information. Now, how do we interpret this and make out of it a practical tool for engineering systems? Go back to the math. In the Bayesian model, the true initial state is a random variable, assumed normally distributed with a known mean, and this is the initial estimate, and the given covariance matrix. So x at 0 is Gaussian distributed, mean x hat, covariance p. This is the mathematical definition. And the chi-square test, or the normalized initial estimation error squared, x tilde 0 transpose p inverse x tilde, should be less than some constant C1, say the 95%, based on the 95% confidence region for the chi-square distribution. That's nx degrees of freedom. Now, sometimes you have to choose the initial covariance, an arbitrary choice, and you have to do it in a smart way. What you want is that this equation is satisfied. If you have a large error in the initial estimate, and the filter is told that initial estimate is highly accurate, such an error will stay in the system for a long time because it leads to low filter gain. Remember, small error means new information is less valuable. Therefore, the filter will operate with a low gain. So the new information weighting is too low. That's not good. So to make sure this does not happen, in the one-dimensional case, we can make the following statement. The initial error should be not more than, say, twice the associated standard deviation, the 2 sigma error. If the initial variance is such the initial error is 1 sigma, and the subsequent measurements are accurate, the initial error will decrease rapidly. So what we have is a way to choose the initial sigma if we have what amounts to a bound on the initial error. Cover the initial error by 2 standard deviations of what you tell the filter to start with in its initial covariance. And this definitely will provide the filter with what I would say can be called honest information, consistent, statistically consistent initialization. Now, in simulation, and we will have to do in many cases an extensive number of simulations, there is a slight discrepancy between what the Bayesian model says and what the engineering common sense tells us. Let's look at it. The Bayesian model for initialization is the initial state is a random variable, and you have a prior PDF of the initial state known and assumed Gaussian. So, what should we do? in simulations, we should generate the initial state with a random number generator according to the distribution about the known initial estimate and covariance. So, the initial estimate is, according to the Bayesian model, a known quantity together with the initial covariance matrix. It's all good and nice, rigorous, but not appealing. Because the true initial state really defines the scenario. What is the scenario? Where that object starts moving from. What is the initial velocity of the object, and so on. So the true initial state defines the scenario, will be different in each simulation. So we really don't want to have a set of simulations starting all from the same initial estimate with a randomly generated initial true state. That's because we are interested in a fixed scenario. Okay, so consequently, a more appealing approach is the following. We choose the initial true state, we choose the scenario, fix it, and we generate the initial estimate according to x hat, Gaussian, with mean x and covariance p. Why can we do it? The role of the initial state and the initial estimate, if we look at the Bayesian model, we have a prior probability of the true initial state given the initial estimate, p of x given x hat at time 0. This is Gaussian, argument x0, mean x hat 0, 0, covariance p 0, 0. But we know the shape of the Gaussian function is an exponential. The form is exponential in the square of the difference between x and x hat. So now we can write this, can be written as Gaussian with argument x hat, mean x, covariance p. So we switch the roles of the random variable and the mean. Now x hat is a random variable and x is the mean, which is fixed. So this is really the PDF of x hat given x. So the special form of the normal distribution allows us to have a fixed scenario defined by x at time 0, and the initial condition x hat 0, 0 is a random, and there's nothing wrong with it. But that again requires a little bit of flexibility in thinking. Now, how do we implement practically things in tracking? The practical implementation of the initialization can be done as follows. You don't have to generate the initial state estimate with a random number generator. There is a simpler way of doing it. We'll look right now at a system where you have the state components, one position, one velocity, in a generic coordinate psi, and assume we have position measurements. Z at k is psi k plus wk. And now assume you get a position measurement at what we designate as k equal -1 and k equals 0. You have two consecutive position measurements, one at time 0, one before at time -1, and we have these noises, wk, Gaussian, 0 mean, as if the sensor gives us the first two noises with its covariance, whatever that is, R. Now, we can designate the initial state estimate psi hat 0, 0 as the first measurement. We can calculate the initial velocity by differencing those two measurements. That's called two-point differencing, and divide by t. And now we will have a 2x2 block of the initial covariance. For the position is r. For the velocity, this is a 2r over t squared, because each of the position measurements has a variance of r. This is for a scalar r, obviously, here. And divide by t squared. And because the position and velocity use both measure the measurement at time 0, there is a correlation between them. So the covariance between the position estimate and the velocity estimate at time 0 is r over t, because a noise comes from here, divided by t, so that's expected value of the error, the product of the two errors is r over t. And then we are guaranteed consistency in the initialization of the filter, and we start updating the state at k equal 1. So the filter really starts at k equals 0, initialized, and the first recursive update is done at k equal 1. It should be mentioned that here equation 5 does neglect the process noise. It can be added by modifying it slightly, as a problem asks you to do it. Now, if several Monte Carlo runs are made, the same initialization procedure has to be followed with new, and again, I'm stressing, independent noises generated in every run according to the same technique, and you cannot and should never use the same initial conditions in Monte Carlo runs, because this will lead to biased estimates. Again, in some cases you have to, then you just have to be careful in interpreting the results. Now, there's another way of doing it, one-point initialization. This assumes there are 2 points. The variance in some problems of the velocity obtained from the 2-point differencing might be much larger than some known bound on the speed. That's because the two sample points, the sampling interval t is very small. In such a case, one can initialize the position from a single observation and use 0 as the initial estimate for the velocity, and choose a standard deviation equal to, say, half of the known maximum speed. So what you do now is you will have 0 estimate, because you take the 2-point difference and gives you a value that might be way too large. The variance is way more than what you know is the maximum speed. Therefore, you choose 0, you don't know which way the initial velocity is pointing, estimate it as 0 and give it enough standard deviation to cover the maximum in all directions. But what this does is will cause a bias in the Monte Carlo runs, because you have a fixed scenario and a fixed initial estimate. So now whatever you have is going to be starting always from the initial condition that is fixed for the scenario, and same initial condition, same initial estimate for the velocity. So you'll have a bias. You should expect some bias in this case, because you don't have a new random variable generated for the initial estimate. So some care has to be exercised in this case when interpreting the results. Now, there's another way of doing it. You can have what is called automatic startup without any initial estimate. There is a technique to start up a filter without initial estimates, and that's called the information filter. And this is discussed in chapter 7, which in this course we don't have time to cover. Effectively, what it does is the information filter does not estimate x hat, but the covariance P inverse times x hat. And would that covariance, if your initial information is nothing, you assume you don't know anything prior to the first measurement, you take that information state P inverse x hat equal to 0, and it turns out the filter can start from 0 and picks up the measurements, and after a while the P inverse is not 0, because when P is infinity, no prior information, then P inverse is 0, then P inverse x hat is 0. But as information is obtained, the P becomes invertible, and then one can switch from using the information filter to the standard state estimation filter, which is more convenient because it estimates exactly what we are interested in. But you can still run the information filter forever, and every time you have to calculate some expression that will map the state in the information filter to the regular state. So you have to multiply it by the covariance matrix. To summarize filter initialization, the error in the initial state estimate has to be consistent with the initial state covariance. And when we choose an initial covariance, it should be such that the error is at most twice the corresponding standard deviation. Now, according to the base set assumptions in the Kalman filter, the true initial state is random, the initial estimate is fixed. It is convenient in simulation to reverse this point of view by fixing the initial state, the scenario, and generating the initial estimate with a random number generator as follows, would mean equal to the true state and covariance equal to the initial state covariance. But even this is not very convenient, so in practice the initialization can be done from 2 consecutive position measurements if the state is position and velocity. If it's position, velocity, and acceleration, you need 3 such states. So in this case with position and velocity only as the state, using the latest measurement will be the initial position estimate. Differencing 2 of them will yield the velocity estimate after dividing by t, obviously, and we can calculate the corresponding covariance matrix. What this is nothing but a first order polynomial fit to 2 points. A high order polynomial fit can be used if the state includes higher derivatives. And this initialization method should be followed in Monte Carlo simulations, where with noises independent from run-to-run, one will then obtain initial errors also independent from run-to-run. In some circumstances, 1-point initialization is appropriate if the variance obtained by 2-point differencing is much more than what you know is the maximum value. Then you are better off using 0 and choosing the standard deviation as outlined above.